Welcome, students. For this last video of Chapter 13, we will look specifically at colligative properties, which is the properties of solutions and how they may differ from pure solvents. So let's go ahead and get started. So, colligative properties. While a solution may be very similar to a pure solvent, it is often distinctly different. And what is special about a colligative property is that colligative properties do not depend on the identity of the solute. So the idea that potassium chloride dissolved in water is no different than sodium chloride dissolved in water, no different than magnesium chloride dissolved in water, so long as the total amount of ions are the same. Because the colligative properties are only disturbing the intermolecular forces and not necessarily affecting the reactivity. So it just matters how much of something is dissolved, not what is actually dissolved. That equal amounts of ethanol and sugar can have the same effects so long as they're equally molar. So the four properties we will look at individually are vapor pressure, boiling point elevation, freezing point depression, and osmotic pressure. But the idea here is that these solutes are, because of the intermolecular forces between the solute and solvent, they are going to resist changes to the solvent. They are going to kind of put a little blockade, making it harder for the solvent to escape, either via evaporation to form vapor pressure, or to escape straight up boiling. So they're going to keep them in the liquid phase. They will break up the perfect crystal structures of the solids, making it more difficult for them to freeze. So the freezing point will drop down. They will encourage the solvent to move in order to dilute their strength, dilute their concentration via osmosis. So that's going to generate an osmotic pressure. So looking at the first one, vapor pressure. The idea here is by mixing a non-volatile solute into an otherwise volatile solution, we can stabilize it through the vapor pressure reduction. The idea is that the entropy of mixing, that randomness, and the added intermolecular forces will help keep the solvent, the volatile solvent, into the liquid phase. Now, it's a real simple equation, and that is Raoult's law for an ideal solution. Raoult's law says the pressure, the vapor pressure of the solution, is equal to the mole fraction of the solvent times the pressure, or the pure pressure that solvent would normally have. So the vapor pressure is going to be reduced by whatever mole fraction it is. So we're going to take the pure pressure of the solvent and multiply by its mole fraction to get the pressure from that solution. Another way to look at this is we can say the reduction in the vapor pressure, the change in the vapor pressure, is going to be equal to the mole fraction of the solute times the pressure of a pure solvent. Now, this works best in an ideal solution. An ideal solution, unlike an ideal gas assumes all gases have no intermolecular forces, no van der Waals forces. Well, an ideal solution assumes all all parts of the mixture have identical intermolecular forces, that like a dipoles are all of equal strength, that the hydrogen bonding, everything has hydrogen bonding, or essentially, so that we're not going to see a stronger attraction or weaker attraction that could cause variance. But it still models it pretty nicely. In fact, I may not ask you to go through this, but the idea is that when we mix two volatile compounds together, the resulting vapor pressure will always be less than the sum of their individual parts. So if we had a vapor pressure of 30 torr and a vapor pressure of 20 torr, if you mix them together, they're going to be like a vapor pressure of 22 torr, something like that. You would expect a total vapor pressure of close to 50, but in fact it's lower than both of them individually, what you would expect. That's because the vapor pressure of A is equal to the mole fraction of A. The vapor pressure of B is equal to the mole fraction of B times its thing. The idea is that the sum of these two vapor pressures are always going to be much less than the sum of the pure vapor pressures. And with that in mind, once we have the, you could calculate the mole fraction in the gas phase by taking the vapor pressure of A divided by the total pressure of them. So this process here we're discussing here is useful for also distillation. The idea that we can separate two things of different boiling points, of different vapor pressures, based on distillation, that fractional distillation, well, some portion of A will evaporate and some portion of B will evaporate, but maybe more of A evaporates first, and then over several distillations you can purify A from B. So just looking at the math, not actually doing it here, but if I took 30 grams of ethanol, which has a mole fraction of, would be 0.65 moles, it has a pure vapor pressure of 5.95 kilopascals. And if I took 15 grams of methanol, which would be 47 moles, or 0.47 moles, and it has a much higher vapor pressure of 1302. So if I figure out the mole fraction of ethanol, that's about 0.58. And so because the mole fraction of ethanol is proportional to the mole fraction of methanol of 0.42, we can figure out the partial pressures of each. So the pressure that ethanol is going to produce is dropped from 5.95 to 3.45. The partial pressure of methanol will have dropped from 1302 to 5.47. And now if I add those two portions up, I get a total pressure from both gases combined of 8.92, which is less than just methanol by itself. Still more than ethanol, but less than you would expect. You would expect something to be something like 18, almost 19. But instead, we get a partial pressure of 8.92. Then if we want to figure out, well, what fraction of ethanol is in the gas phase? Well, 3.45 over 8.92, so about 0.387 mole fraction. So as we distill them, we can separate ethanol from methanol. The gas phase is enriched in methanol, and as we allow that to condense into another container, we would have different moles of each, and so would have different vapor pressures, and we could keep distilling that until we completely separate the methanol out. Now, another property, this is one that is far more useful, is boiling point elevation and freezing point depression. Just like with vapor pressure, solutes will cause the change in the temperature which freezing and boiling can occur. The equations are as follows. Our delta T of boiling is equal to the Kb, it's an elevation constant, times the molality. The point at which a solution boils is based on a constant times the molality. So how much solute is dissolved in this such a boiling point thing, and that's going to affect how much the temperature is increased by. Similarly, the change in the freezing point will be equal to negative Kf, and the negative constant, times the molality of that same solute. So if I have a 1 molal solution of sugar in water, we would expect a drop in freezing point of 1.86 degrees C. That's because the Kf for water is 1.86. And so we would expect it to freeze at not 0, but negative 1.86. If you add more than 1 molal, it's going to drop again, further and further and further. Now, Kf and Kb will almost always be given for a solvent. It's something you could look up on a homework problem, but typically it is given unless the problem itself is asking you for to determine them. You cannot find them otherwise. But these Kf's and Kb's are solvent dependent. So they do not depend on what is dissolved, they only depend on what is doing the dissolving. So water has its own 2 values, but it only needs those 2 values to describe all situations of water. This freezing point depression will be useful if you have to take organic chemistry later on and you need to know the purity of your solid, because it will melt at a lowered temperature depending on the purity. How much the drop in the melting point directly depends on how much impurity is present in your solid. The last property is osmotic pressure. Solutions desire to be homogeneous. They want to be well mixed. And so they will work and strive to achieve this. If a solution is separated through a semi-permeable membrane, that our pores are just big enough to allow the solvent through but not the solute, solvent will naturally migrate from a pure solution to a pure solvent to a solution phase to try to get the molarity just about equal on both sides. This process is called osmosis. Now, this will create a difference in the volumes both internally and externally between the 2 sides. Now, if you were to stopper this and calculate the force of the pressure applied that the water is trying to get in through osmosis, you would generate essentially the osmotic pressure. That we force it back down, you would figure out the osmotic pressure that is being generated here in this U-tube. The equation is simply put osmotic pressure, which is pi, capital Greek letter pi, is equal to the molarity times our gas constant R times temperature. Molarity is, of course, moles over volume, so the units of R will generate our pressure. So temperature obviously has to be in Kelvin. Now, this is an important effect in many biological systems. If both sides of the membrane are equal, no osmosis will occur. This is an isotonic solution. But if the outer solution is significantly more dilute, then you have that means the inner solution is more concentrated. We have a hypotonic system, and water will flow in and sometimes cause the cells to burst. If the solution is far more concentrated, the cells will shrivel up as water flees them. This is a hypertonic solution. These are both extremely dangerous. Hypothermia and hyperthermia are also dangerous to the body. So can hypotonic and hypertonic solutions be. This basic process also explains why freshwater fish often can't swim in salt water and vice versa. Their body has a certain concentration of salt, their cells, and they can manage under certain saline conditions. But put them in a completely different salinity, and you look at a hypotonic or hypertonic situation. It takes special types of fish to be able to survive in both conditions. So we have a couple problems left of practice and a few more things. So this problem right here, if 75 grams of benzophenone, so C13H10O, is dissolved in 500 grams of benzene, C6H6, but it's a solvent. It's our solvent. It doesn't really matter what its molar mass is. With our solvent having a boiling point, T boiling of 80.1, and a K(B) of 2.53. What temperature would the new boiling point occur? What temperature would the new boiling point occur? So with that in mind, the equation is delta T boiling is equal to K sub B M. We're given K sub B. Delta T boiling would be the T final minus the T initial. All we need to find is our molality. Our molality, well, we have 500 grams of solvent. So that's 0.5 kilograms. We just need to find out what is our molar mass of this. So 10 plus 16 plus 12 times 13. So what is our molar mass of this? 12 times 13 is 156. Plus 10 plus 16 is 182. 182 grams per mole. So how many moles do we have here? Grams in 1 mole. 75 divided by 182 is about 0.4121 moles. So our molality would be 0.4121 moles divided by 0.500 kilograms, which is 0.824, we'll say 2 M. So K sub B, which is 2.53, which is degrees C per M, and we're multiplying this by 0.8242 M, would give us a change of 9 degrees C. So when does the boiling point occur? T sub F minus 80.1 equals 209. So the boiling point, our T final for the boiling would be 82. Let's say 2 degrees. It's not a huge change based on that concentration, but it is a change. Freezing point depression often has a greater effect, but boiling point elevation does have a minor effect. Now, what is more impressive is electrolytes in colligative properties. Because remember, the colligative properties does not care about what is dissolved, just the sheer amount. Well, the previous examples assumed a non-ionizing, non-electrolytic solute. So something that would dissolve but not break apart. So most non-electrolytes are organic compounds, such as non-metal hydrocarbons. But colligative properties depend on the quantity of the solute. So if something were to ionize into cation and anion, there would be a multiplicative effect, one where you increase by the amount of ions produced. So most of our problems will include what's called the Van't Hoff factor, a small letter I. And that I is some ratio of the moles of particle in solution over the moles of solute dissolved. Now, in non-electrolytes, that I is assumed to be 1. But in salts, we need to add up the total number of cation and anion pairs. So, for example, sodium chloride, you would expect an I to be about 2, 1 sodium and 1 chloride. Calcium chloride, you expect it to be 3 because you have 1 calcium, 2 plus, and 2 chloride, 1 minus. On potassium phosphate, you would expect it to be 4. So because 3 K pluses and 1 phosphate 3 minus. Remember that phosphate itself stays together. So you would not see a I of, in that case, 8. You would not see an I of 8. You would only see an I of 4. So remember, only consider the ion pairs, not the total number of each element. So ammonium nitrate would be NH4, NO3 would only have an I of 2. Because ammonium is 1 and nitrate is 1, so they only add up to 2. So with that in mind, our new colligative equations look like this. The delta T sub F equals negative I KFM. The delta T sub B is equal to I KBM. And our osmotic pressure is I MRT. Now the vapor pressure depression, you would consider the ionization when considering the mole fraction, but that rarely is the case. Sometimes you need to consider that, but it's a little trickier. We won't usually deal with that. But so, to finish us off with last 2 problems. How many grams of calcium chloride would be required to melt 1 kilogram of ice, 1 kilogram solvent at calcium chloride at 7 degrees, negative 7 degrees C? K sub F is 1.86. Let's start with that, and then we'll come back to this. So, this one is asking us to work backwards. So, delta T sub F equals negative K sub F Y K sub F M. The first thing is I want you to be able to figure out what amount of salt would you need to melt that much ice. So at 7 degrees. So negative 7 is minus 0, which is the freezing point of ice. It's going to give us negative 7. And that's going to equal to negative I with calcium chloride, 1 and 2. You have 3. Your K sub F is 1.86. And so, M. So with that in mind, what is our M? we're going to take our 7, negative 7. We're going to divide by our 3, our negative 3, and divided by our 1.86. So we got an M of 1.25, and we'll say for molal. That molal is equal to moles per kilogram. Well, in order to melt 1 kilogram of ice, we would need 1.254 moles of calcium chloride. If I want to figure out the mass, calcium is about 40. Chlorine is about 35, we'll say, and a half. And there's 2 of them. So we'll say that's about 71 plus 40. So total molar mass of something like 111. So take our 1.254 moles times 111 grams per 1 mole. 254. And you would get, I only need 139.2 grams of calcium chloride to achieve 1 kilogram of ice melting at negative 7 degrees. So it takes very little amount of ice to depress the melting point by that much. So look at this again. Let's see, PowerPoint. Now the second one. What osmotic pressure in ATM would be generated by a molarity solution of 0.75 molar of sodium chloride at 25 degrees? If R is 0.08206. And so our equation is osmotic pressure equals IMRT. Well, I, for sodium chloride, 1 and 1, would expect 2. M is something that we've already given at 0.75 moles over liters. R is 0.08206 ATM liters per mole Kelvin. Moles, liters. And we need, finally, Kelvin. So 25 plus 273 is 298 Kelvin. 298 K. K and K, this is going to give us pressures of atmosphere. So, solution of 0.75. So times 2 times my R, 8206, times 298. Gets a surprisingly powerful pressure of 36.68 atmospheres. That is very powerful. That's enough. I mean, in terms of pressure, that is very intense. However, that assumes a pure solution on the other side. Most times it's not a pure solution, so there's going to be 2 opposing osmotic pressures. But that is the last bit of this chapter. So with that in mind, 36.68, I will leave you for today. Have a good day.